Welcome to lecture 15 of, we're still in unit 2 here. We're still solving higher order ODEs. And so in lecture 14, we learned how to solve homogeneous linear ODEs, usually second order ODEs with a majority of what we solved, with constant coefficients, okay? So now we know how to solve some of these homogeneous equations in the very specific case that the coefficients are constants. Well, we should also learn how to solve non-homogeneous equations. So equations where the right-hand side of the differential equation is non-zero. Now there are multiple methods that we are going to learn in this class to solve these types of equations, but the first and ultimately the easiest, in my opinion anyway, is the method of undetermined coefficients. And so if you are able to use this method, and I'll explain to you when we are and when we are not allowed to use this method, but when you are allowed to use this method, it's often a good choice because it's probably the simplest method. Okay, and we're going to use this method a lot, both in Unit 2 and in future units where we're solving non-homogeneous ODEs in perhaps slightly different ways. So let's recall from earlier in the class, I think it was about 3 lectures ago, we talked about non-homogeneous equations, and we said that we can write the general solution to an ordinary differential equation as a sum of 2 parts, okay? So here we have our ordinary differential equation, L, this differential operator L. So this can represent many different types of linear ODEs. But you notice that the right-hand side of the ODE is equal to some function of x. Okay, so if this is a non-zero function, then we have a non-homogeneous ODE. Okay, so recall we can write the solution to this ODE as the sum of a complementary term and a particular solution. And recall that this complementary term, this complementary function, solves the homogeneous version of this ODE. So YC, the complementary function, solves L of y equals 0. Okay? And if it so happens that this ODE has constant coefficients, well, now we know exactly how to solve this homogeneous equation. Okay, YP represents a particular solution to the non-homogeneous ODE, and we know that we can write y of c as the superposition or the linear combination of a fundamental set of solutions y1, y2 through to yn. Okay, so we learned this a few classes ago, and then in the previous class we learnt how to solve ODEs with constant coefficients, linear ODEs which are homogeneous with constant coefficients. We learned how to find YC. So now we want to know how can we find this particular solution YP now. Okay, and as I said, the first method we're going to learn is the method of undetermined coefficients. Okay, so the idea is quite simple actually. The idea is to try a particular solution YP of the same form or the same type as the function, the non-homogeneous term g of x, so the right-hand side of the differential equation. So it's quite a simple idea, and in fact the application is simple. The algebra can be a little bit tricky, but the method itself is a fairly simple idea. So let's learn this method by example. So we're asked to find the general solution to the ODE y double prime plus 3y prime plus 2y equals 1 plus 3x plus x squared. This is obviously a second order linear equation. It is an equation with constant coefficients, so therefore we know how to solve that equation. We know how to solve the homogeneous version of this equation. We learned that in the last class. And the right hand side of this, or let's say the non-homogeneous term here in this ODE, well, I could write g of x is equal to 1 plus 3x plus x squared. Okay, so I know that I can write my general solution to this ODE as the sum of two terms, a complementary function and a particular solution. So let's begin by finding the complementary solution. So recall this is the y of c, the complementary function solves the homogeneous equation y double prime plus 3y plus 2y equals 0. So now we're looking at the homogeneous version of the ODE we were given. Well, I can immediately write down the auxiliary equation for this homogeneous case, right? It's going to be m squared plus 3 times m plus 2 equals 0. I can solve for the roots of this quadratic to find the solutions of this auxiliary equation, and it's not too hard to show that the two solutions are real and distinct, and the values of the roots are -1 and -2. And so therefore, because I've memorized the three cases for a homogeneous linear ODE with constant coefficients, I can immediately write down that the complementary solution is just some constant c1 times e to the -1 x plus some constant c2 times e to the -2 x. Okay. So finding the complementary solution is fairly straightforward, especially if you practice and recall the types of solution that occur in both case 1, case 2, and case 3. So that was from lectures 13 and 14. However, to find the particular solution, we're going to try using this idea that we've introduced here of the method of undetermined coefficients. Okay, so let me clean up my slide here. What I'm going to do is I'm going to try a particular solution which is the same form as g of x. Okay, so as this 1 plus 3x plus x squared, so a quadratic. So I'm going to say my particular solution that I'm going to test is going to be equal to a plus b times x plus c times x squared. So because I have a quadratic, my function g of x, my non-homogeneous term is quadratic, I'm going to try a quadratic as my particular solution. Okay, well, I want to use this, test this particular solution in the ODE, so to do that I'm going to need two derivatives, right? I'm going to need y prime and y double prime. So I should differentiate this, this quadratic, which is very easy, of course. I'm just going to get b plus 2 times c times x. And then to take another derivative, it's even easier. I'm just simply going to get 2c. Okay, so now I want to use these expressions for the particular solution and its two derivatives here in the original non-homogeneous ODE. Okay, and so if I do that, use these terms in the non-homogeneous ODE. If I do that, then I get y double prime is 2c. Y double prime is 2c plus 3 times y prime, so 3 times b plus 2 times cx, plus 2 times y, so 2 times y up here, equals the right hand side, equals g of x. Okay, great. So now I've used my test or my guess solution, particular solution, in the ODE. And so now I need to find the values of a, b, and c here. Okay, and what I can do is match terms to find the values of a, b, and c. So for example, rewriting the equation here that I've derived, I can look at the x squared terms. Okay, so on the left hand side of the equation there is only one x squared term here. On the right hand side, again, there's only one x squared term, so it's not too hard to see that c is going to be equal to 2 times c times x squared equals x squared. 2 times c times x squared equals x squared, so c is going to be equal to 1/2. Okay, so now let's look at the x terms now. So the x terms on the left hand side, well, I have 3 times 2c here, so 6c times x here. I've got 2 times bx is here, and I've got 3x on the right hand side. So if I write that out, I get 6 times c plus 2 times b equals 3. Okay, but I already know the value of c. C is just a half, so really here I've got 3 plus 2b. So 3 plus 2b equals 3, just matching the x terms there. So obviously from this equation it's pretty clear that b must be equal to 0, because I have 3 here already, and I have to add 0 to make sure that stays equal to 3. And so I can play the same game with the constant terms. So now the constant terms on the left hand side, I've got 2c here, I've got 3 times b here, but okay, b is 0, so I can happily ignore that, and plus 2 times a here, so 2a here, and that has to be equal to 1. Okay, so I've just written that out here. B is 0, c is 1/2, so this is actually 1 plus 2a equals 1, so therefore again 1 plus 2a equals 1, again a is going to be equal to 0. So therefore the particular solution that satisfies the original non-homogeneous ODE is quite simply c times x squared, or 1/2 x squared. Okay, so now I originally found the complementary solution, and now I've found the particular solution. So to find the general solution to the ODE that we started with, I have to just simply sum these together. So my complementary solution was c1 e to the minus x plus c2 e to the minus 2x, my complementary solution. And then I've just shown that the particular solution to this non-homogeneous ODE is 1/2 x squared. Okay. So great, we can solve these, at least certain types of non-homogeneous ODEs now. So, well, there are a few caveats, so we'll look at some of those. Okay, so the method of undetermined coefficients, the method works for certain types of non-homogeneous functions g of x. Okay, it doesn't work for every g of x that we can think of. Okay, so it works for what I'm calling Pn. Basically, Pn is just some nth order polynomial. So for any nth order polynomial where the an's, an minus 1, a2, a1, a0 are just constants. So any nth order polynomial, this method is actually a really good method to apply to the non-homogeneous ODE, to solve the non-homogeneous ODE. Similarly, a polynomial times an exponential, again where a is some constant and p of n is just the nth order polynomial, the method of undetermined coefficients works really well for a polynomial times an exponential. Similarly, it also works for a polynomial times an exponential times sine of b of x, and polynomial times an exponential times cosine of b of x. Notice I did not say the tangent here, so it does not work in the case of a tangent with b of x. And even though, for example, in these last two terms here, I've said polynomial times exponential times cosine or sine, well, the polynomial could just be 1, a here could just be 0, so the method also works for just pure sine or just pure cosine as well. Okay, any other kind of function, which of course there are many, for example the log of x, any other function on the right hand side other than what we've displayed here will require a different method to solve the ODE, to solve the non-homogeneous ODE. And we will learn a few of these methods in a future class. Okay, so let's just add this information to our screen at the top here, just to give myself a little bit more space. So the method of undetermined coefficients is a way to find a particular solution to the non-homogeneous ODE. The idea is we try a particular solution of the same form as g of x, and the method works for this particular set of g of x types. So a few caveats to this, a few things that we need to keep in mind, that we need to remember. Okay. firstly, if g of x is an nth order polynomial, and if this nth order polynomial has some zero terms, we still have to use the full nth order polynomial as a test function. Okay, so for example, if my right hand side g of x was just x squared, there's no x terms, there's no constant terms, it's just x squared, then my test function y of p still should be a times x squared plus b times x plus c. We still need to include those lower order terms in our test solution, and we'll show some examples of that soon. So y of p, the particular solution, should still be the nth order polynomial, even if some of these a terms are missing in g of x. Secondly, if our non-homogeneous term in our equation is, let's say for example, some constant times the cosine or some constant times the sine, so if we have some cosine or sine term on the right hand side, even though there's only one of these trigonometric functions present in each of these functions, we still have to test y of p equals some constant times the cosine plus some constant times the sine. Okay, so even if I don't have a sine in my g of x at all, but I have a cosine, my particular solution which I need to test should have both of these terms in it. Okay, and if you miss one, then you're basically not going to be able to solve the system, or at least not guaranteed to be able to solve for the value of the constants. Okay, and then the third note here, which is also very important, if any terms in the trial expression for yp are solutions to the associated homogeneous equation, so if we first solve for that complementary function yc, and let's just say for example we get e to the x as one of our solutions, well, if g of x is also e to the x, then we can't just use yp equals e to the x. We have to use x times e to the x, okay? So our trial expression for yp should not be a solution to the associated homogeneous equation. If it turns out that x times yp is also a solution to the homogeneous equation for some reason, then we are going to use x squared times yp, and so on. It's very unlikely you'll have to go any higher than x squared times yp, but it is possible, and there's no problem taking x cubed times yp and so on. So let's look at some examples of what I'm trying to say with these three notes here. So we have the ODE, the obviously linear constant coefficient non-homogeneous ODE, y double prime plus 9 times y equals 2 times cosine of 3x. Step 1, of course, is to solve the associated homogeneous equation. Okay, so the associated homogeneous equation is just set that right hand side equal to 0. I can easily write down the auxiliary equation for this homogeneous equation. It's just simply m squared plus 9 equals 0. I can easily solve for the roots of that quadratic, and of course you can see already it's going to be an imaginary number. So the first root is going to be 3i, and the second root is going to be the complementary 3i. So if you look here, the real part of the root here is 0, so alpha is 0, beta, the imaginary part, is 3. So because I know my three cases by heart now, I can write the complementary function, or the solution to the homogeneous equation, as y of c equals some constant c1 times 3 of x, cosine of 3 of x, plus some constant c2 times the sine of 3 of x. Okay. So again, not too hard to solve the associated homogeneous equation if you've memorized the three cases that we went through in lectures 13 and 14. Okay, well, now we need to find the particular solution yp, but you can see here already there's some small issue that the cosine of 3 of x appears on the right hand side of the non-homogeneous ODE. Okay, so I'm just going to move my my complementary solution up here out of the way. So here is my complementary solution to the homogeneous equation, associated homogeneous equation. So equals 0, the right hand side equals 0. Okay, so even though g of x contains the cosine, we would try a particular solution of the form a times cosine x plus b times sine x. So we have to include the sine term here. Okay, so that's the first note. Just because we have cosine on its own, we still need to include the sine term here. But again, as I pointed out before, this particular solution has the term cosine of 3x, which is a solution to the complementary function. Okay, it's a term that occurs in the complementary function. So therefore, we have to choose, instead of yp equals this expression here, we have to choose yp equals x times this expression here. So we're going to try this particular solution, y of p equals x times a cosine 3x plus b sine 3x. Okay, so 2 points here. Just because our function g only had the cosine, we have to also include the sine when we use the method of undetermined coefficients, and vice versa. If there was only a sine here, I would still also have to include the cosine. And secondly, because cosine of 3x, so one of the terms in the particular solution, appears in the complementary function here, then we must multiply this y of p by x. Okay. So we have our test particular solution. Now let's take two derivatives of that. Okay, well, it's a little bit of a pain because we have a product rule here, but it's not too hard, right? So let's firstly differentiate x and keep the bracketed term constant. So we just get a cosine 3x plus b sine 3x. And then secondly, let's keep x constant and differentiate the bracketed term. So that would be x times negative 3a times sine of 3x plus 3 times b times cosine of 3x. Okay, so again, I'm assuming here that you're quite comfortable with your differentiation rules. If you're not, again, I would just really suggest getting a lot of practice, as much practice as you can with that. Okay, well, I also here need a second derivative, right? In fact, I don't really need the first derivative apart from to calculate the second derivative, because the first derivative doesn't even appear in the ODE. But okay, well, again, this first term here is relatively easy to differentiate. The second term, I'm also going to get a product rule because I have x times sine and x times cosine. So if you differentiate that second line there, that first derivative of the particular solution, then I come up with something that looks like this. And of course, it's not too hard to do, but it is a lot of writing. So it will take a little bit of time to write this down. So now I can actually simplify this line, right? Because I can notice that there is a times sine of 3x here, so there's a negative 3 of them there. And there's also a times sine of 3x here, so I can simplify that, and there's similarly b times cosine of 3x, b times cosine of 3x. And I can rewrite this this as the second derivative of the test particular solution is as described here. And so now I want to use this expression for the second derivative of this test particular solution in the ODE and y as well, so the particular solution yp here, in the non-homogeneous ODE. So if I do that, if I use these in the non-homogeneous ODE, I get a long term here which is representing y double prime. I get plus 9 times this particular solution yp, this test particular solution yp, and then of course I get the right hand side here as well. So there are a number of simplifications that I can make. Happily, this term here, negative 9x times all this stuff, is going to cancel with this positive 9x times the same stuff here. So in fact, these two terms are going to cancel. which greatly simplifies my ODE, or my equation. So I end up with negative 6 times a sine 3x plus 6 times b cosine 3x equals 2 times cosine 3x. Okay, well again, now I need to match terms. I need to match the sines on the left and right side and the cosines on the left and right side. And it turns out that, of course, there are no sine terms on the right hand side, so a must be equal to 0. There are two cosine 3x terms on the right hand side. There are 6b on the left hand side, so therefore b must be equal to 1/3. And so then we can use these values of a and b in our particular solution, our test particular solution, which remember was, if I go back, it was x times a, which, well, a is now 0, so this term disappears. So we basically have x times b, which is 1/3 sine of 3x, and that is our particular solution. Okay, let me scoot back to this point here. So we can write the general solution of our non-homogeneous ODE as the sum of the complementary function plus the particular solution. So in green here I have the complementary function that we found right at the start, and I just showed you that the particular solution was 1/3 x times sine of 3x. So again, this method is fairly easy to visualize, or let's say imagine, or even use, but the algebra can be a little bit tricky. And again, you just need to keep in mind these 3 notes that I pointed out before. Let's look at another example here. So I have another second order equation with constant coefficients, linear equation with constant coefficients. It's non-homogeneous. We have this term 8x multiplied by e to the x here. But as always, we're going to approach it in the same way. We're going to solve the associated homogeneous equation, y double prime minus y equals 0. So my auxiliary equation is going to be m squared minus 1 equals 0, which has the solutions well, it's pretty easy to see that this is going to be 1 plus or minus 1. So 2 real distinct roots to this quadratic. And again, because I know my case 1, 2, and 3 from lectures 13 and 14, I can write down my complementary solution as c1 times e to the 1x plus c2 times e to the negative 1x. Okay, so pretty easy. Hopefully this is becoming second nature for you now, solving these homogeneous constant coefficient equations. Step 2 is find the particular solution. Okay, so particular solution, we want to try a yp of the same form as g of x. Okay, so what is the form of g of x here? Well, I have a polynomial, 8x, times an exponential. Okay, so that is our second term here that we're allowed to use the method of undetermined characteristics for. Except we have to keep in mind that whenever we're using a polynomial, we have to use the entire polynomial. So this is a first order polynomial here, so we should try the particular solution equals a times x plus b times e to the x. Okay, so even though multiplying the e to the x on the right hand side, or the g of x here, we only have x, we don't have a plus a constant. When we try the particular solution, we must have this plus the constant here. So a times x plus b. Okay, but now there's another problem, because a times x times e to the x, okay, I've circled the wrong thing, but a times x times e to the x is a solution, is a solution to the non-homogeneous equation. Sorry. B times e to the x is a solution to the non-homogeneous equation, okay, because the non-homogeneous, the complementary function that we found before, yc, was equal to c1 e to the x plus c2 e to the negative x. So this term we have here appears in the complementary solution here. Okay, so we have a problem here we have to multiply our y of p by x. Okay, so therefore we're going to try a particular solution of the form x times a to the x plus a times x plus b times the exponential of x. Okay, so now we have the test form of our particular solution. We can now obviously take its second derivative, well, first by taking the first derivative and then by taking its second derivative. I'm going to skip through this quite fast because I think it's a relatively easy product rule to take derivatives of. Again, you should take the time to work through the details here. I'm going to also leave it up to you to substitute y double prime into the ODE and y into the ODE to match the terms and hopefully find that a equals 2 and b equals negative 2. Okay, so therefore the general solution to our ODE we've presented here is the complementary solution we found by solving the homogeneous version of that ODE, plus the particular solution we found with the value of a equal to 2 and the value of b equal to negative 2. Okay, and so notice here that we had this particular solution x times ax plus b, even though we didn't have a x, this polynomial was first order, but it was missing the constant term up here. As it turned out, we needed the constant term to be able to solve the system. Okay, so just to summarize here, the method of undetermined coefficient works for polynomial for non-homogeneous terms of this form here that we already introduced. It does not work for more complicated functions of g. For example, the log of x, 1 over x, tangent of x, or even the arctan of, it should be x. So for these types of non-homogeneity, we will need to learn some new methods, which we will in a future class. Okay, well, thank you for your time, and if you have any questions, please get in contact with me or post on the stream forum, and I will see you in the next class.